Now, what I want to use here is this equation, now as nasty as it could possibly be, actually can be written down as a formal solution. I don't have to solve the initial value problem. There's actually a direct map from my initial condition to the endpoint. Okay? And that one is a matrix exponential. Okay? E to the TL solves that equation. So this is the one shot that takes me from the initial condition all the way to the end of the time interval Q of t. Okay? So what we do is we seek an initial condition that optimally amplifies over a specified time interval. That's like a stability analysis, but certainly not in the Lyapunov sense, because we have a finite time interval, and we want to see how bad can it get over that time interval. Okay? If you take that time interval t here and take it to infinity, yes, you would recover the Lyapunov stability. Okay? But as I said, this in most flows, this doesn't make sense. The time scale is set by the flow, and we're going to have a characteristic time step, time horizon t, and we want to know what is the perturbation over that time step, time horizon t, that optimally grows and uses all it can use in the equations to grow. Okay. So now my iterative scheme is actually not going iterative anymore because I have a direct map. Okay, so my forward integration, my governing equation, is now just an algebraic map between my initial condition and what comes out at the end of the integration. But I don't integrate, I just map. Okay, the adjoint can also be solved because now the adjoint also is linear and can be mapped the same way. And that's the solution to my second block. The adjoint equation is another map that takes my outcome from here and maps it back to 0. Okay? Reverse integration in one shot. Okay? There's no need to do time stepping. And then my third box was the gradient expression, right? I stick all of that into the gradient expression, and what comes out? An eigenvalue problem. An eigenvalue problem from the linear, where the initial condition is actually appearing as an eigenvector, and the gain is appearing as the eigenvalue squared. And this exponential is L and L plus together, so this is the full round trip. Okay? Forward is for L, backwards is for L plus. You stick one on top of each other, you go one round trip. So you start at 0, the L takes you to t, the L plus back to 0. These two together is one round trip from 0 back to 0. Okay? So that's the combined mapping of one round trip. And what you do here is you write down an eigenvalue expression, and what that adjoint looping, this going around and around and around is doing, is basically a power iteration on that eigenvalue problem. That's all there is. Okay? Now, if you break this one apart, so suddenly linear algebra is doing the optimization for us. Okay? So you should be aware of that one. When you calculate eigenvalues or singular values, you actually solve a very specific optimization problem. Okay, keep that in mind. So this one, if you break that apart, this is e to the TL times e to the TL plus. Okay, so it's a little bit like form like A times A transpose. Okay? And an eigenvalue of an expression like this is the same thing as a singular value decomposition of just one of those components. Okay? And here it is, the SVD of the matrix function. That is classical non-modal analysis. Okay? You take the matrix exponential, you hit it with an SVD, the singular values give you the maximum gain, and the principal left and right singular vectors give you the best input and the best output. Okay, so this is a special case of that optimization around and around. Okay, second case, let's say we want to have a outside forcing. Okay, so we want to know how does our linear system respond to some kind of a frequency input. That could be an acoustic wave in a free stream, that could be roughness distribution on the wall, anything you want. Okay. So now this is our governing equation, but again an LTI system with linear time invariant system matrix. And now our objective is, okay, I want to play around. My control variable is how do I force? And my objective that I measure with is the energy of the response divided by the energy of the pumping. Okay? So this is the internal amplification of the system, given a certain frequency. The frequency you dial in, that's a parameter. Just like before it was the time horizon. Okay? So this is what you have. So we want to see what frequency resonate with our system in a sense, but I don't want to overuse the word resonance. Okay? It has a bad connotation. So we seek an external driving that produces an optimal response at a specified forcing frequency. And just like before, this thing doesn't need to be integrated or time-stepped. It's linear and time invariant, so that means I can actually write down an equation for that one that maps it directly from forcing to output. And that one is like this. The matrix resolvent does that. Okay? So I omega minus L inverse maps the forcing directly to the output. Okay? So no integration there either. And then you can go through the same thing, okay? Since this is my box for the governing equation, no integration, a direct map with the resolvent. This is my adjoint equation, no integration, a direct map between the response and the adjoint forcing, okay? Then you stick everything into the gradient box, okay? And again, you get an eigenvalue problem. The forcing, the control variable, the forcing comes out as an eigenvector, and the gain comes out as an eigenvalue squared. Okay, and this is the forward mapping, and this is the backward mapping, just like before. Linear algebra is doing all that optimization for us. Okay, and the same thing. The SVD of the resolvent gives you everything you want. The singular values will be the H's. And the singular vectors will be the QFs and the QRs. Okay, one shot. So you probably have seen this thing. You may have even done these things, but there are actually special cases of an optimization that is much, much more powerful than being restricted to LTI systems. Okay, so little summary. What you probably learned in a hydrodynamic stability course, if you learned Orr-Sommerfeld equations and things like that, Rayleigh criterion, inflection points, and so on. This is modal analysis. So that means we're looking at the eigenvalues of matrix functions. But you should remember that this is a T to infinity analysis. You have to judge whether that makes sense for your flow or not. Okay? Mostly it doesn't. The few cases where it does make sense or you get away with it are very, very rare. Okay, so that's modal analysis. The next more general thing is non-modal analysis. You have a finite time horizon that makes already more sense, but you can only apply that one to linear time invariant systems, but you replace the eigenvalues by the singular values of the same matrix functions. E to the matrix exponential, or the resolvent, or there's many other ones that you can use. Okay? So that's already a generalization. But the best generalization is to let go of almost everything and go optimization based with that direct adjoint looping. Okay? And then you have finite time, you have nonlinear, you can handle nonlinear equations, time-dependent systems with the tool of choice, which is that direct adjoint looping. And I'm not saying this doesn't take more effort. Sure, the derivation of the adjoint, all these implementation things, the checkpointing, all that costs a little extra, but you get so much more out of it. This is more or less useless information if you have a complex flow. Let me show you a few applications. Okay. So the first one, I'm going to show you 3 applications and a few more, another one later on. That one is tonal noise. This was joint work with Miguel Fosas de Pando from Cadiz and Denis Sip from Honora. So this is the thing. You have an airfoil, NACA 0012, 12 degrees of 2 degrees angle of attack. Mach number is 0.4 and the Reynolds number is 200,000. That puts us into the glider range. Okay, it's not an airfoil. You don't see this phenomenon on a A380. But if you have a glider airplane, that's about the range you have. And if you're a glider pilot, you actually know about tonal noise. Or wind turbines. Okay, the annoying noise that wind turbines make, that's from an instability like this. So this is how it goes. We have an instability of the boundary layer on top, and we have an instability of the boundary layer on the bottom. Okay, these two instabilities roll down and meet each other at the trailing edge, where they slam into each other, high shear. The high shear generates an acoustic wave that radiates in all directions, also upstream, and at some point re-triggers that instability. Okay, so we have a feedback loop between hydrodynamics and acoustics on the top and on the bottom. Okay, two feedback loops talking to each other through the trailing edge. Okay, analyzing that one by doing local analysis, and it has been done and has been published, by slicing the boundary layer here and doing a modal analysis with eigenvalues of the boundary layer here doesn't really capture anything that is essential for this type of mechanism. Okay, so the way we do that one is we're using our sensitivity analysis between the forward solution and the adjoint solution, and we ask the question, given a frequency, so this is the resolvent analysis, given a frequency, what is the most dangerous input? Okay, so if you do that one, this is the most dangerous, this is the optimal response, the things that come out that are stimulated at a specific frequency the most. Okay, and you see that this is a modal solution, or this is a coherent solution that has all the features that we're actually expecting to contribute. So it has the boundary layer instability on top. Here it's rolling down. There's also a boundary layer instability here, but it's so small it only amplifies almost on the last little piece here. You see it here. Okay, so it doesn't do anything, and suddenly, whoop! In the last one, it really goes up. Then you have the acoustic wave radiating, nice dipole here, radiating forward and triggering it again. Okay, so now if I ask you about the origin of this process, okay, because this is the process with the highest acoustic component, that's the loudest mode we found. Okay, and if I ask you, where does this thing come from? If I want to kill this one and make the airfoil more quiet, what should I do? Where should I place something? The regular stability analysis has nothing to say about that. You have to actually go to the sensitivity information for this structure and see where its adjoint lives. Okay, and this is how the adjoint looks like. This is it goes backwards in time, as I said. Okay, so this is the sensitivity information for this mode. Okay, so disturbing this one, people have tried to put little bumps up here to disturb that boundary layer instability up there. Did not make a difference at all in terms of making it more quiet. Okay, sometimes it even made it louder. Okay, but then there was a long time ago there was a Japanese technical report that never made it into the main literature. They put a wire and put the wire, just traversed with the wire from here all the way to there and down on the bottom. And when they came to this spot here, suddenly the airplane went totally quiet. Okay? So if you want to kill this one, this is the question for the origin of an instability or the weakest link in the feedback loop. The adjoint and the sensitivity information actually gives you that information. This is the place where you put the wire or a bump or something or an actuator to kill this one. And this is the weakest link of that feedback loop. And it's not on top. It looks like something is happening on the top. That's just the sideshow. Okay? The real sensitivity is in the bottom. Same thing goes for, second example, a boundary layer receptivity. Let's say we have a boundary layer, very, very classic. Many papers written about that one. And you have a bump here and a bump there. And you have a compressible boundary layer. Okay? Mach 0.3, Reynolds number of 1,000,000. And you want to know something about the resonance, acoustic resonance between these two bumps, okay, and how to manipulate that one. This is the part that you have from the forward problem. It's unfortunately not animated, okay? So this is the same thing. This is the forward problem. This is the first box. This is the second box with the sensitivity that goes with it. And if you superimpose the two, you actually get, as you expect, a frequency response that has these peaks, okay? So everything here, when it peaks, there's a constructive interference between these two. The two waves constructively interfere and amplify each other, okay? Then for other frequencies, the wave number from here to there doesn't fit in a integer multiple between the distance, okay? And that's why you get a trough here. And then it fits constructive, destructive, constructive, destructive, and so on, okay? So the nice part about that is also, this was calculated with the direct and the adjoint. The adjoint has the sensitivity information, okay? It has the sensitivity information to any changes you make with the equation, okay? So we have the Q plus, and we have the Q, and now we can play with the equation any way we want. That means we can now say, without any more simulations, without any more calculations, we have everything we want. We say, what happens if the Reynolds number goes up by 5%? Well, we just take all the terms in the equation that are multiplied by the Reynolds number, and we take our solution for the direct problem in the adjoint, we evaluate that scalar product, and we know what will happen. Okay? Then we say, okay, how about changes in the Mach number? Well, we take all the terms that have Mach numbers in it, okay, and multiply it, and so on and so on. So what we did is we wanted to know if we change the distance between the two bumps, what will happen to this curve, okay, the amplification. And usually what you have to do is you take the bump a little bit further, you do the whole thing, the whole calculation again, and then you get a second curve, okay, and then you see how that second curve changed. But since we have the forward and the adjoint problem, we have everything we need. So our delta F are all the terms that make this distance larger. And this is the curve we get. This is the change in G, in that amplification, divided by the changes in the distance between them. Okay, this is the curve we get. And we get that just by evaluating that expression. No new simulations, no new stability analysis. Okay? So once you have that, if you look at this one, wherever that thing has a peak, it's going to go through 0 here. But it's on the left side of the peak, it's always positive. On the right side of the peak, it's always negative. Okay? So this is the first term of the Taylor series expansion. If I multiply that one by delta xd, I get the delta g that I can add to my curve. So if I do that one, I know that all the frequency peaks move to the left, okay, without doing that calculation again. And I can play around with that with any changes I can make to the equations. Okay? So there's a lot of information in that adjoint. It's worth calculating it because then afterwards you can ask any question you want about parametric instabilities. All right, third example, spark ignition. That's joint work with Ubay Quadri from Cambridge. So the question here we had is, let's say you have a flame and the flame blows out. That's a very dangerous condition for a pilot. You're up there, engine goes out, you need to restart the engine. Okay, you better, if it's a fighter pilot, you want to have it restarted on the first trial, right? So you want to do it as best as you can. Okay, maybe a commercial airliner can try a few times, but a fighter pilot needs to have an engine to get away. All right, and we also use the optimization-based framework. Okay, so here's just a simulation. That's what happens. We can have a little spark here. Okay, and the first thing is the kernel generation. So it's a little hotspot, if you want. Okay, then the whole flame expands. Okay, it reattaches back to the nozzle. Okay, so it attaches here, and then it blows to the right, okay, until it reaches the domain, okay, flame expansion, and then it sort of bounces back, and then eventually the flame stabilizes and settles into a nice flame, back reattached to the nozzle, okay. So the question is, where should we put that sparker so that we can get to a fully established flame as quickly as possible, okay. So our cost objective is the integral over a specific time to if we integrate that curve here, we want to have as big an area as possible underneath it. Okay. And then we go around and around with that direct adjoint thing. Here's a spark, okay. And then here is the forward simulation. The whole thing blows out, okay. Then we're going to stop that. That's the time horizon we picked, okay. Then we go over here, and then we propagate that one back with the adjoint reactive compressible Navier-Stokes equations, okay. So as I said, this is a reverse in time. So first it blows out, and then the adjoint sucks it back in, okay. And by the time we get to 0, out of this mess here, we extract the gradient of how to move this point so that next time we're going to go through that process a little faster, okay, and a little steeper in that curve, okay. And you build that up and up and up, and then here you have all the iterations, and you see that the iterations nicely follow the stoichiometric surface as they should. That was just a little bit of a test problem. Now we're doing a lot more complicated configurations in a lifted jet diffusion flame. That's work in progress. All right, so this one brings me then to a few extensions. Okay, so these were like a little bit like bread and butter applications of that framework, the optimization-based framework. So what else can you do? Can we actually push it even further than we already have? Okay, and the nice thing you can do about that one is here we have the objective, here we have our equation constraints, and I reverted back to linear time invariant just for convenience. You can just as well write a nonlinear equation here and do the same thing. Okay, so don't be too stuck with that. Okay, so we have two things that we can actually do. The equations are always the same, okay? So there's not much we can do here. It's already good that we can enforce the nonlinear equations. So let's see what can we do here and what else can we do. So we can impose a different norm here. This is the 2 norm. This is the energy norm, okay? The energy after time t divided by the energy it had before. And by doing the energy, it's sort of the go-to norm for incompressible flow. If you don't have any better idea how to measure a perturbation, you say energy. Okay, energy is nice and L2, but it has some disadvantages, and that one is because we harvest energy, we're not restricting the size of the initial condition or the size of the output. Okay, so by saying maximize the energy, the structures usually spread anywhere in the flow field wherever they can get some energy. Okay, they can get their hands on some energy. Okay, so usually energy is linked with shear. Just by displacing shear, you can actually create energy. Okay, so if you have an optimization and there is a big shear layer that goes really long, like a separation bubble, you're going to get a structure that spans the entire separation bubble, okay? Because since you maximize energy, it really takes every little bits and pieces that are available from the flow to create as much energy as it can, okay? So these structures got pretty big. But sometimes in practical applications, we're not so interested in these large structures. We want to do a worst case analysis. We want to see where in the flow is a dangerous spot, okay, that generates a localized disturbance that is dangerous in terms of growing. Okay, and the large ones are often growing better, but they're just a little bit too contrived. Okay, so we want to change the norm here. We want to measure this part not in a 2 norm, but in something else that compactifies our input and our output. Okay? So changing the norm is a big thing because I have a sketch here. So let's say our constraint is somewhere on that line. So that means all the solutions that satisfy our equation are on that line. And that line is always the same because the equation is always the same. But based on how we measure the objective, which is the closeness to the origin, that depends on how we measure closeness. Okay? And if you do a P1 norm, then this is the solution that is optimal. If you do a 2 norm, this is the solution that is optimal. And you see that if you do an infinity norm, this solution is optimal. So you have a solution, but it slides up and down your admissible space. Okay?